Okay, this is going to be a lesson on calculating and interpreting the average rates of change for a graph over different intervals. These are the answers to last night's homework questions. Take a minute, check your answers if you didn't last night on Edline. Please make a note that we are going to, for homework tonight, is SLT 9 Flexbook, the Explore More questions, numbers 5 to 10. And today's lesson will mainly focus on standards of math practice number 2, to use number sense when representing our problem, and standard of math practice number 6, which is to be precise with words, numbers, units, and symbols. The units today is going to be particularly important. So here we go. Everyone grab your packet and open up to SLT 9, which is titled A Beach Trip. Take a minute, read through the scenario with your group, and answer as many of those questions as you can. Might be a good time to pause the video. Okay, so the average speed for the first hour, what's kind of funny is that these answers are right here. If they drove in the first hour 54 miles, their speed was 54 miles an hour. If the second hour they drove a total of 67 miles, they drove 67 miles per hour. And then that last hour, anyone who's driven to Ocean City, Maryland knows, you start to hit traffic, you slow down a little bit, that's actually not too bad, 43 miles per hour. So the next question is, what is the speed over their entire trip, the average speed? Well, to do that, we're going to need to add up what they traveled in the first, second, and third hour, and then divide that by 3. So if we add up, we find that wherever these people left, it was about 64 miles to Ocean City, which makes about sense, and 3 hours. And if you divide that, you get 54.6 repeating. We'll make it 54.7 miles per hour. I forgot to mention, you can have a calculator out for this lesson because some of the computations are kind of tedious. All right. What is the average speed of the car over the last 2 hours of the trip? So if we eliminate the 54 and we say 67 plus 43 over 2 gives us 110, gives us 55 miles per hour. Is it possible that they ever reached a speed of 100 miles per hour? So for that, I'm going to say it is possible, but highly unlikely. And the reason I'm saying this is because if they were able to accelerate to 100 miles per hour, they would have to slow down very quickly so to maintain the average speeds found above. Because, like, think about it, if you were trying to pass someone and there was a good straightaway, you probably could, like, zoom up, but then you would have to slow down right away because you'd be approaching the next car in front of you. So it's possible, but I'm going to say it's highly unlikely. How can you tell if they stopped for lunch? Well, there are 2 ways you could tell. One is they wouldn't have covered, I won't say moved because I typed an M, moved as far in that hour, and the average speed would go down. Now I want you to take a second and think about what would this look like on a graph? I don't want to say go down, that's a bad word, I'm going to say decrease, that's a better math word. On a graph, we would see a constant horizontal section where they didn't increase their distance because they stayed in one spot. Now, if it was a speed graph, the speed would go all the way down to 0 and just stay there. But either way, we would see a horizontal section of the graph. All right, this is what I would like you to do. Everybody turn the page, and I want you to examine the graph that's labeled SLT 9A. And I'm going to put some questions up, and I want you and your group to just consider those questions for a minute. So here's the graph you're looking for. It's titled A Change of Pace. It's SLT 9A in your packet, and these are the questions I want you to answer. Like, who is moving the fastest? Okay. This is difficult to agree on because for a little while the dotted line appears to be moving faster, and then at 1 second it tapers off. What additional information would better help you answer this question? Well, that first graph that on mine is kind of a blue color right here. On yours it's kind of like the lower curve. It goes up really high, but you don't know what happens after this point. Here, I'll highlight it for you. You don't know what happens here. Like, after this, what happens, I don't know. I'm assuming it continues in that direction, but that's an assumption. I'm not given any functions here. I don't really know what's going on. All right, how would you describe the behavior of each function on the interval 0, 1? Well, on the interval 0, 1, they move at different rates, but they all cover the same amount. And you're not given any units here, so on the interval 0, 1, all we can really say is they have the same average rates of change. I don't know if it's that they all cover the same distance or they're all traveling at the same speed. Like, I don't know, maybe it's a time speed graph. Maybe it's a time distance graph. I don't know. All I know is they have the same average rate of change. Who has the greatest average rate of change for 0 to 0.5? That would be the lowest graph. On yours, it doesn't, you can't see the color again, but it is supposed to be the navy graph. So like right here, see it's navy, and the line is red. So I'm going to say, oh, I know how I'll say the solid curve does. Solid curve. No, the greatest. Whoops, my bad. The dotted curve. And the reason I know this is it has the steepest slope. Who has the greatest rate of change on from 0 to 1.5? So for that one, I'm going to definitely say the solid curve. Because it has the steepest slope at that point. And I hope you see what the key word is here. In general, how could you determine which function changes most rapidly on any interval? Find the slope for that interval. Now, I'm going to start you off on SLT 9B, and then you are going to be on your own with your group for the rest of SLT 9B. So everyone go ahead and turn the page. All right. So the average rate of change is going to be the total amount of change over that interval. So for those of you who feel like it's been forever since you have taken Algebra 1, it may be a good idea to remember our handy dandy formula for slope. There we go. Okay, so here we go. So this is SLT 9B, and it says use your graph from flipping Ferraris to solve each problem. Now, just as a reminder, flipping Ferraris was, I have it here, SLT 8. So we have some equations. It says determine the average rate of change on the interval 0 to 100. So the first thing I'm going to do is I'm going to flip back to SLT 8, and D of S is 0.03 S squared. So if I wanted to determine the average rates of change, the first thing I need to do is calculate D of 0, which is 0, and the distance Is D for distance? I forget. Yes. Grab your calculator because that's just a lot. I mean, you could probably do that one, but then it's going to get a little painful. And we find out that that is 300. So, to calculate the average rates of change, we really have two ordered pairs here. We have 0, 0. We have 100, 300. So, y2 minus y1 over x2 minus x1 is just going to give us 3. Specify units, that's our standard of math practice that we're working with today, number 6. So I'm going to flip back to, everybody flip back to, again, to flipping Ferraris. And check the units. How are we measuring distance? We're measuring it in feet, which makes a lot of sense. Feet, and how are we measuring speed? Miles per hour. Okay, and so this is pretty much how we are going to go through the rest of SLT 9B. So go ahead and with your group, finish SLT 9B. I'll put the answers up in a minute. Actually, no, I won't. Sorry.